used two pieces of information to sketch out the fact that the slope 4 is positive and the c term is 1. So this is y equals 4x plus 1. Okay, we can see here from what's called a concavity that for small values of x, this is bigger than 3 to the power of x, but eventually the 3 to the power of x is bigger. Okay, so it says use substitution to verify that f of x is smaller than g of x for x equal to 1.9. So this is just a calculator jobby. So at 1.9, we're going to see using a calculator that the value of f is smaller than g. So what this question is about is it's going to be showing that, okay, eventually the exponential function is bigger than the linear function, but and in fact it's probably easy to see where if you substitute x equal to 2 into these, 4 times 2 plus 1 is 9, 3 to the 2 is 9, so at 2 they're equal, but after that the exponential is always going to be bigger. And you can play, well, you can try and play a similar game with any power, anything that's a polynomial sums the powers of x. So anyway, let's answer the question as that. Have we drawn the graph? Yeah. Part 2 now, use substitution that f of x is smaller than g of x for 1.9. So f of 1.9 is 3 to the power of 1.9. Now you can mess around with this. This is, what is it? The 10th root of 3 to the power of 19. But we'll just use a calculator here and we'll estimate it. So what that means is we will just use a few significant figures. So I'm going to do 8.06 is probably enough for me here. Now it's not equal to 8.06, so I like to do an approximation. G of 1.9 meanwhile is 4 times 1.9 plus 1, and this one I'll probably be able to do in equals. 4 by 1.9 plus 1, and I get 8.6. Now it's important to answer the question that's asked. Verify this, so this basically does it. Yeah, you could just say therefore g of 1.9 is bigger than f of 1.9, which is, we can see from this picture. Right, now it says prove using induction that the value, and I think this possibly is a mistake here. No. So it's saying that we want to prove that for all natural numbers, so for 2, 3, 4, 5, 6, so on, that this is bigger than this at natural numbers. Now it will actually be also equal at all other numbers, but we won't think about how we're going to solve that. We won't do that. So we have to show that. Now they're using f of n and g of n. How about we do, well, what is f of n? It's 3 to the n, and that it's bigger than or equal to 4n plus 1. Okay, now it's an induction. Now you shouldn't know straight away how to do it. Like I actually don't know to answer how I'm going to do this, but I'm going to set up my induction anyway. So let Pn be the statement that 3 to the n is bigger than 4n plus 1. And this is, for each natural number n, this is the statement. So what we're going to do is we're going to show the base case. Now, the base case is going to be easy. We've actually nearly shown this already. Then we're going to assume that it's true for some number. And then we're going to show from that that it's going to be true for the next number as well. Now, you, in my opinion, you need to understand induction. It's not that complicated. I'm not going to do a video about it, but it's an idea that you need to understand completely, in my opinion. Okay. See how's the camera looking? Okay. Yeah. Okay. So the base case here is we're asked to show it actually for n greater than or equal to 2. It's not true for, well, this is funny. It is actually true for n, it's not true for n equal to 1. Okay. But anyway, n equal to 2. So let's look at P2, question mark. So P2 says that 3 to the power of 2 is greater than or equal to 4 times 2 plus 1, and that is true. Okay, so the base case is true. Now assume pk, that is for some or any, well, assume for, let's say some or any, I'll just say k, a natural number, and it'll have to be bigger than or equal to 2, a natural number, which I want to write down here, that 3 to the power of k is greater than or equal to 4k plus 1. Now what we have to show in deduction is that, assuming this, we can show that the next thing is true. The next proposition is true. Now how I do this, now what you definitely can't do is start putting in k plus 1 here, that's wrong. So what I recommend doing is you go to rough work. You write down what you're required to prove and maybe see where it might come from. So what you're required to prove is pk plus 1, which is that 3 to the power of k plus 1 is greater than 4 times k plus 1 plus 1. Okay? So one of the things you can do with this is 3 to the k by 3 equals, and then this thing, if you multiply it out, it is equal to 4k, that's the 4 by the k, the 4 by 1 gives you a 4, I'll keep that back. Okay, now I don't know is this necessarily going to be the way to do it, because the problem here is, okay, what are you doing on the left hand side? You're multiplying by 3, and on the right hand side you're adding 4. And how are you sure, like, you probably can argue that multiplying by 3 and adding 4, that multiplying by 3 increases the left hand side by more, but that's not really what we want to do. What we probably want to do is start with this and multiply both sides by 3, because then you'll get this. And can we show maybe that 3 of these is bigger than this, which shouldn't be an issue. So park this part of the rough work and try and do something else. If I multiply both sides of this by 3, what do I get? I get the 3 to the power of k plus 1, and I get, if this is true and I multiply both sides by 3, I'll get here 12k plus 3. Now this should be possible to show that this is greater than 4k plus 5. That should be no problem, because this is equal to, take the 4k plus 8k, that's splitting up this, plus 3, and because k is, it's actually bigger than or equal to 2, in particular it's bigger than or equal to 1, so this thing is actually bigger than 11, and so you have 4k plus 11, and this is certainly bigger than 4k plus 3. So this actually ends up being pretty much the proof, but this is in the rough work. This shouldn't go on your question paper here. I don't know how much, as I said, I can't remember much, I don't know much about the Leaving Cert as it happens today, but presumably you have rough work at the back. Presumably you can ask for extra paper. I know if it was me, I'd be asking for extra paper, and I'd be figuring out something like this at the back. Now we can write down our thing. So we're going to multiply both sides of this by 3. So if this is true, if this is greater than or equal to this, I can multiply both sides by a positive thing. I can multiply both sides by 3, and I get another true inequality. So I end up with 3 times 3 to the k greater than or equal to 3 times 4k plus 1. And now I just repeat what I did here. So this is equal to 12k plus 3, and this is equal to 4k plus 8k plus 3, and this, we know that this is actually greater than or equal to 11, because k has to be greater than or equal to 2. So I mean, in particular, I could actually take this to be 19. So this, if this is greater than or equal to 11, this is certainly greater than or equal to 4k plus 5, because 11 is bigger than 5, and then this is equal to 4 times k plus 1 plus 1. So assuming pk, you have that pk plus 1 is true. So this means that pk plus 1 is true, and using induction, this shows that Pn is true for all n greater than or equal to 2 and a natural number. Okay, which is what we're asked to do. Having answered the question was asked, prove using induction that one of these functions is bigger than the other. Yeah, we've done that. Okay, let's move on. Probably a harder question than the previous two. So on to question 3. Factorize fully. So this is what I was referencing earlier about how I factorize quadratics, and this is kind of related to it. So it's when you got these 4 terms. So they want us to factorize 3xy minus 9x plus 4y minus 12. And it's a similar story. You take out what's common out of the first 2, and then try and take something out of the second 2 so that you're left with a third actual common factor. Sometimes you have to take the common factor out of the first and the third term. I can't predict when that is, but you just try it with the first 2. So if I try it with the first 2, a common factor here is 3x. And what am I left with? I see y minus 3. And then I need to take something out of these 2 that leaves y minus 3 again. And presumably you can see that it's 4. And then you take out the common factor of y minus 3. And you're left with 3x plus 4. Now this is a good example of reading the question, how I answered the question I was asked. A lot of students, I feel, would go on to solve this equal to 0 and say, oh, y is equal to 3 or x equal to minus 4/3. But it doesn't ask us to solve it equal to 0. It asks us to factorize it, and we have done so. So that's that question answered. Part B. So part B is asking us to use this. Let's see. It gives us a function, kind of a complicated function. G of x is equal to 3x log x minus 9x plus 4 log x minus 12. Now I have to say, and they want us to solve this equal to 0. Now I'm not sure what this question is about. Perhaps it's about just pattern spotting, so that you can see how this falls into this framework where the y is, presumably it's quite easy to see that the y is log of x. It'll also use the fact that one of the things that's very important in maths is that it's difficult to say when a sum is equal to 0. Like if you try and do it in your head, you make the x too big, then this will get very big and you'll be away from 0. Make the x too small, you get similar issues with this minus 9x. So it's a big principle is that it's difficult to say when a sum is 0, but it's easy to say when a product is 0. So if you want to say when a sum is 0, you should factorize it. And here it's kind of already done. It might be a bit difficult for us to see this. So these are the 2 things this question is interested in. So presumably using part A, because it says using your answer to part A or otherwise. If you weren't to use part A, I really don't know how else you'd do it. Now presumably it's possible, but I don't know. Well, we're just going to use this. The y is clearly log x. So this is the same as y minus 3. The y is log x, so it's log x minus 3 times 3x plus 4. And that kind of pattern spotting, I think that's a difficult skill to learn. You just need to do loads of questions and start seeing patterns. The next part is mathematical. You've got 2 numbers multiplied together giving you 0. Either this is 0 or this is 0. The same principle is behind why you factorize quadratics. One of the reasons is because it's a quadratic, which is an x squared and x and a constant, that's a sum. It's difficult to say when that's equal to 0. So one of the ways you could solve it is to write it as a product, in other words, factorize it. The other way, which is using the formula, comes from something a little different. It's called completing the square. And I imagine that you've seen that in your studies. Okay, we've got 2 little equations here. So the first one is this one. So as you've seen how you've got two numbers that are equal, apply the same function to both of them, they'll still be equal. So you just have to identify what's in the way and get rid of it. So for me here, this minus 3 is in the way. So I will be adding 3 to both sides here. And that gives me log of x is equal to 3. Now what you have to do is you have to understand what is the inverse function of log. What is the function that undoes the action of log? So the inverse of log is exponential function. So I apply the exponential function to both sides. Exponential function of log x just gives me x, and then exponential function of 3 is e to the 3. Perfectly good answer. It's not asking me to give decimal places or anything. I'm just going to leave it like that. It's a perfectly good number. If you want to round it, you can. Why? And then here, I want to get x on its own, so work from the outside like an onion. I want to get rid of the plus 4. What's the inverse of adding 4, taking away 4? And I get 3x equal to minus 4. And then the x is multiplied by 3. What is the inverse of multiplying by 3? Dividing by 3. So I'll divide both sides by 3. And that should be the question. And sorry for standing on the wrong side of the whiteboard there. Okay, so that's that question done. There's nothing more to it. Does the answer make sense? Presumably. Ooh. So there's something interesting here. Something a bit funky goes on. Interesting at looking at the solution here. The exam paper solution. I'm gonna do it. I might pause the video soon and do it. Have I answered the question that's asked? Have I solved g of x equals 0? I have. Does my answer make sense? Different question. Now, in your context questions, you know, like you or say in your probability, you don't want to get negative probabilities. But with an equation, what you do is you check your answer. And I made a remark earlier when we were looking at the exponential function that log of a negative number is undefined. So if you check your answers, well, this one might work for you. This is not a solution because log of minus 4/3 is undefined. Now it might be the case. It might be the case that, okay, so there's different definitions of log for negative numbers and stuff, but look, here we're not talking about them. This is not a solution. So the answer, in fact, is x equal to e to the 3. So for my own selfish reasons, I'm going to pause the video now and I'm going to see what did the marking scheme do about this. Yeah, so sure enough, no reference in the marking scheme to the fact that this is actually not a solution. My advice is not to worry about such things too much. Like there's a kind of concept of mastery. Like I should be able to be very good at the leaving cert paper, etc. What I would say to you is that if you did know something like this in the paper, just write it down. Maybe say why. I haven't written down, and I would say that doing so, the people who mark the leaving cert paper are mathematicians, and they should know that log of minus 4/3 undefined. And what that will do is it'll communicate to the examiner that you really know what you are talking about. But look, if you don't see that, the people writing the marking scheme didn't even see that, so don't worry too much. Okay. Right, next question. So the next thing is looking for the derivative of this at e corrected 2 decimal places. So we need to differentiate this function. We've got some options here, I think. We can certainly differentiate this. And we have a little product rule. I think there's an argument to be made that it's possibly easier to differentiate this. Much of a muchness, I suppose. I think I'm going to differentiate this. So off we go. So now, because this is two things multiplied together, we need the product rule. And so we get g dashed of x equal to the first thing, which is log of x minus 3, times the derivative of the second thing. Now, what I recommend is when you're differentiating a sum, you do it term by term, fixing constants. So what I would recommend here is that you fix the 3, and the derivative of x is 1, plus the derivative of 4 is 0. Plus the second thing, which is 3x plus 4, times the derivative of the first thing. And the derivative of log of x into your tables is 1 over x. And then the derivative of minus 3 is 0. And now we can evaluate this at e. This may or may not be easier, I don't know. Now you should know, and of course your calculator can tell you, if you don't know this, that log and exponentials are inverse. And what that means is ln of e is ln of e to the 1. And the log undoes the exponential, so that means that ln of 1 is just 1. Sorry. ln of e is 1, excuse me. So this is 1 minus 3 times 3, plus, here you got 3e plus 4 by 1 over e. Now normally I wouldn't approximate at all, but it's asking for 2 decimal places, so we'll do it. Ever just go to the calculator. A lot of calculators have an e on them.